Welcome to Tomorrow Unveiled.
The week we're diving into today, December 11th through the 18th of 2025, it just felt different. It wasn't just a busy week for the space industry. It was more like a fundamental phase shift.
The phase shift.
Yeah, it felt less like a series of, scattered experiments and much more like the sound of a vast, complex engine finally roaring to industrial life. Like it's finally hitting its peak operational speed.
Okay, let's unpack that moment.
Yeah.
Because for years we've been tracking this new space age, right? It's been all about bold private companies and this rapid, almost frantic technological growth.
Right.
But the sources that our dedicated research team compiled for this, they clearly mark this specific week as a real transition point, the end of, let's call it, the experimental space age.
And the official beginning of the industrial, autonomous, beyond Earth era. That's exactly it. This isn't just, incremental growth.
Yep.
It's a change in tempo, a change in technology that just forces us to rethink, well, everything, from material science and orbital mechanics all the way up to global security policy.
And that's the critical insight we really want you, the learner, to grasp from this. Our mission here in Tomorrow Unveiled is to connect those dots.
Exactly. To connect the dots between, say, a new White House policy, a revolutionary breakthrough in material science, and then the grim reality of traffic management in a dangerously congested orbit.
And to be clear, we've synthesized a really comprehensive set of sources, but we're focusing exclusively on the findings that were strongly cross-corroborated, the things the research team found in all the data points.
And things we know are happening.
Exactly. So our key question today is pretty simple, but I think it's also profound. What does it actually look like when the space industry operates at an industrial tempo? And what's the hidden cost?
The hidden costs.
Because based on this data, the cost to just get to orbit is collapsing, is making space accessible to almost anyone. But the cost of staying in orbit and making sure that environment stays clean and usable for the future.
That's skyrocketing.
It's skyrocketing. And that tension right there is what's defining this new era.
It is. So let's start with that industrial tempo.
Let's do it. If the space industry were a global supply chain, this past week was the proof that the assembly line for orbital delivery is now fully automated, it's incredibly efficient, and it is running non-stop.
And the most visceral, almost boring proof of this new reality is just the sheer success of reusable rocketry.
Boring success, I love that.
It is. Monotonous success is the perfect description. For anyone who follows launch schedules, a Falcon 9 flight used to be front-page news.
Oh, absolutely. A major event.
Now it's a weekly event, sometimes multiple times a week. And when we look at the data our research team collected, one specific statistic just defines this shift. A SpaceX Falcon 9 booster, B1SOC3, completed its 30th flight on December 17th.
30 flights for a single booster. It's still hard to wrap your head around that number.
It really is.
It wasn't that long ago the rockets were these bespoke, multi-million-dollar, one-and-done artifacts.
Use it once, throw it in the ocean.
Exactly. Now they're crossing thresholds that put them on par with commercial airliners. They're demanding a level of reliability and predictability that we only associate with mature transportation sectors.
And that's the strategic context that really matters here. This booster, which was only the third ever to hit that 30 flight mark, it proves reusability is no longer experimental. It's not technically risky anymore.
It's the standard.
It is the undisputed industrial standard for medium to heavy lift. When you can reuse a critical, complex piece of hardware like a first-stage booster 30 times, you just fundamentally rewrite the economics of getting to space.
So what does that rewriting actually look like on a balance sheet? What does that mean in practice?
Well, it shifts your spending. It moves it from capital expenditure, or CapEx, to operational expenditure, OpEx. So instead of building a brand new $60 million booster for every single mission,
which is insane.
It is insane. You're now spending relatively small sums on refurbishment, on maintenance, on really detailed inspections. This reduces your manufacturing bottlenecks, and it drastically lowers the marginal cost per launch.
And the reliability, I have to imagine, plays a huge role.
A huge role. The sheer reliability you get from 30 successful missions, that translates directly into lower insurance premiums for the satellites you're launching.
Of course.
And easier regulatory sign-off for future missions. The market now treats this thing as a reliable asset, not a high-risk gamble.
And the sheer scale of this operation it's just staggering. The research team noted that the company hit its 550th successful booster landing during that same Starlink mission.
550.
And by December 17th, they'd completed 165 Falcon 9 launches for the year, setting another record, with 167 total projected for 2025.
That operational tempo is unmistakable. We're talking about a rocket launching every...
What is that, every 2 or 3 days?
Every 2 to 3 days, on average, globally. And within that staggering cadence, there was this massive local milestone, the 100th Falcon 9 launch from Florida in 2025.
100 launches from a single state in 1 year.
Yeah.
That goes way beyond just having efficient rockets, doesn't it? It forces you to look at the ground infrastructure.
Absolutely.
What kind of friction points does that level of rhythm create, outside of the engineering of the rocket itself?
It moves entirely into logistics and range management. I mean, think about the precision required for that.
The choreography of it.
It's a ballet. You have personnel scheduling across 3 shifts. You're securing massive quantities of propellant cryogenic oxygen, rocket-grade kerosene. And crucially, you're coordinating range clearance with the military and air traffic control.
For 100 launches.
100 launches requires a level of logistical rhythm that's comparable to running a high-volume cargo port or a major airline hub. It signifies that the entire system, government and private, has matured enough to handle the sustained high-cadence operation.
And speaking of industrial capacity, the future for heavy lift, the really big stuff, that just got fundamentally altered too. We saw that critical regulatory hurdle get cleared for Starship operations at Cape Canaveral.
Yes. The U.S. Space Force and SpaceX signed what's called the Record of Decision, or ROD, for the Environmental Impact Statement. This is for Starship ops at the Cape.
And this regulatory approval, it's more than just a rubber stamp.
Oh,
right.
Much more. It sets the ceiling for all future industrial activity there. And the key number here is the permit allowance. It authorizes a truly staggering 76 launches and 152 landings annually.
76 launches, 152 landings, that's what, almost twice a week on average?
Pretty much.
Just for heavy lift, out of a single complex. Given the manufacturing and infrastructure delays we always see with cutting-edge rocketry, how realistic is that tempo?
It's ambitious, certainly. But the approval itself, that signals regulatory confidence in the technology's eventual maturity. The bottlenecks aren't really the rockets anymore. They're the ground systems.
The plumbing?
Exactly. To support 76 flights a year, you need more than one orbital launch pad. You need multiple pads, dedicated assembly buildings for processing the boosters, massive tank farms for methane and oxygen.
A whole city, almost.
You're building a spaceport city. The regulatory sign-off means they have permission to build that infrastructure at scale. And if they achieve that capacity, it fundamentally alters how the U.S. government and commercial heavy users plan their future logistics. For LEO, the Moon, and for Mars, it's the permit you need to build the beyond Earth economy.
And this industrial tempo isn't just limited to one actor's capacity. We also saw massive steps being taken to consolidate competitor constellations.
Yeah.
Specifically, Amazon's Kuiper system.
That's right. United Launch Alliance's Atlas V551 rocket launched 27 Amazon Kuiper satellites this week. This is a really critical convergence of competing technologies and, strategic alliances.
Right.
This launch brings Amazon's operational constellation to 180 satellites, and it's rapidly pushing them toward a massive regulatory deadline.
Which, just to remind our listeners, is the FCC mandate requiring them to deploy half of their initial planned constellation, 3,236 satellites, by mid-2026.
Precisely. That regulatory clock is the master pacer here. It's forcing everyone's hand. So we're seeing companies accelerate their launch schedules, leveraging every reliable vehicle they can get their hands on, from the proven legacy Atlas V, which is still flying, to the high-cadence Falcon 9.
All to meet legal requirements.
All to meet legal requirements. So the key takeaway here is that getting to space is no longer the rate-limiting step. The focus is now entirely on how quickly and how often you can deploy huge quantities of mass to meet geopolitical, commercial, and critically regulatory mandates.
The industry is moving mass, not just technology.
That's the new game.
Okay, so that focus on sheer launch quantity, that's perfect for filling up low Earth orbit. But if we shift our focus from quantity to quality, the source material shows that this industrial age, it requires us to move beyond the limitations of current chemical propulsion. Especially if we want to build a truly permanent presence beyond LEO. We have to go further, faster and much more efficiently.
Absolutely. I mean, chemical rockets are magnificent. They're amazing for escaping Earth's gravity well, providing that huge thrust really quickly. But they are just gas guzzlers in the vacuum of space.
Right.
They're fundamentally incompatible with the kind of energy density you need for fast, deep space travel and for long-duration missions. And this is why the technological breakthroughs this week point so decisively toward the nuclear space age.
Let's dive into that key breakthrough then. General Atomics Electromagnetic Systems, or GAEMS, they successfully tested proprietary nuclear fuel samples under some really extreme conditions.
This is a major, major materials science victory. And the metric here is crucial. The fuel samples were successfully tested at 2600 Kelvin in a flowing hydrogen environment.
Okay, 2600 Kelvin. Let's put that in perspective.
It's incredibly hot. It's over 4,200 degrees Fahrenheit. That is nearly half the temperature of the surface of the sun. So the fact that this proprietary fuel material maintained its structural integrity, its performance in that superheated hydrogen flow, that's the proof that the engine concept is viable.
So why is that temperature and that material resistance so significant?
Yeah.
How does nuclear thermal propulsion, or NTP, how does it change the game for a trip to Mars?
Well, we need a quick translation for efficiency. When we talk about rocket efficiency, we use a term called specific impulse, or ISP.
Right.
Think of ISP like the miles per gallon for a rocket engine. Chemical rockets, even the most efficient hydrogen-oxygen ones, they typically achieve an ISP of around 450 seconds. NTP, by using a nuclear reactor to heat liquid hydrogen to these extreme temperatures, 2600 Kelvin without any combustion, can nearly double that efficiency. It achieves an ISP of roughly 900 seconds.
So if I'm planning a mission to Mars, doubling the fuel efficiency means I can get that critical fast transit time.
Exactly.
That 9-month journey could be cut down to just weeks. That's transformative.
It is, and that reduction is vital not just for time, but for crew health, for mitigating radiation exposure, and for minimizing the overall mission complexity and supplies you have to bring. It moves Mars from this incredibly difficult one-off expedition to a manageable, repeatable logistics problem.
And there's a policy connection here too, isn't there?
A direct one. This technical success directly supports the new executive order mandating the deployment of nuclear reactors on the moon and in orbit by 2030. The government is signaling that the hardware is now ready, or at least nearly ready, to meet that very aggressive policy timetable.
But I imagine there are trade-offs to using a nuclear engine. I mean, beyond just the technical challenge of the fuel itself, what are the secondary industrial challenges this creates?
The primary trade-off is mass. It's always mass. While NTP offers this incredible efficiency, you have to carry a nuclear reactor and all its necessary shielding.
And shielding is heavy.
Shielding is very heavy, which offsets some of your payload gain. This demands heavy lift capacity, which circles us right back to why that Starship 76 launch permit is so strategically important. You need that industrial-scale heavy lift to deploy the nuclear infrastructure.
And safety, I assume?
Of course. The second challenge is ground safety and operational protocols, which just become far more stringent when you're handling reactors and enriched fuel on Earth before you even launch.
Okay, so moving from high-thrust propulsion for these fast trips to efficiency for long-term orbital presence, we also saw progress on the electric front, which is all about endurance.
Right. Specifically for NASA's Lunar Gateway Station.
What happened there?
The delivery of 3 high-power, 12-kilowatt Advanced Electric Propulsion System thrusters, AEPS thrusters, is a quiet but monumental milestone. AEPS is the most powerful electric system ever designed for deep space.
And unlike MTP, which is all about high thrust,
AEPS provides incredibly gentle but persistent thrust, but with extreme, unrivaled fuel efficiency.
so why is that specific form of efficient low-thrust propulsion so crucial for something like the Gateway, which is just going to sit in orbit around the moon?
Well, the Gateway needs to maintain its unique, really complex orbit. It's called a near rectilinear halo orbit, or NRHO, for multi-year missions, supporting Artemis IV and beyond.
And maintaining that orbit requires constant little pushes.
Small, continuous corrections. Exactly. Electric propulsion systems use minimal propellant, often just xenon gas, which makes them perfect for long-duration station keeping. They sip propellant rather than guzzle it.
So it's about endurance.
It's all about endurance. This ensures that the gateway infrastructure can stay operational for a decade or more without needing constant, costly resupply missions. It's what makes permanent lunar access economically viable.
Now let's talk about changing the geometry of spaceflight entirely. This radical disk-sat form factor. Rocket Lab successfully deployed 4 of these novel satellites. This feels like a completely different design paradigm than the traditional boxes and cylinders we're used to seeing.
It is truly a revolutionary design. It's pushing the boundaries of spacecraft architecture. These are plate-shaped satellites. They're about a meter in diameter, but only 2.5 centimeters thick.
A pizza box.
It's a space pizza box. And it's the conceptual opposite of the standard CubeSat form factor.
So why this strange flat shape? What problem does this actually solve for the learner?
So the design is optimized for very low Earth orbit, or VLEO. That's typically orbits below 300 kilometers.
And VLEO is desirable because
The closer you are to Earth, the higher your imaging resolution is and the lower your communications latency. But VLEO is incredibly challenging because atmospheric drag is a huge problem. It rapidly slows you down, decays your orbit, and forces you to use constant propulsion just to stay up.
So a traditional VLEO satellite has a short, propellant-hungry life.
Exactly. But the DiskSat has this inherent advantage because of its shape. It flies edge-on relative to its direction of travel.
Oh.
So it minimizes the surface area that's exposed to the trace atmosphere. Think of it like a knife cutting through water. Minimizing that drag significantly increases its lifespan in VLU, making those high-res orbits practical.
But there's more to it, right? From a sustainability perspective.
This is the genius part. At the end of its mission, it simply flips face on.
So it turns itself into an aerodynamic paddle held flat against the current.
Precisely. That maximizing of drag ensures rapid, passive deorbiting. It's a key debris mitigation feature that's built right into the design. It ensures that even in the most crowded orbits, these satellites quickly and safely dispose of themselves without needing any active propulsion.
It's just good orbital citizenship by design.
That's a perfect way to put it.
And if we want to eliminate chemical fuel entirely, not just for station keeping, but for core maneuvering, we have to talk about xenoastronautics and their advancement of the supertorquer technology.
This is an attempt to take attitude control, so managing a satellite's orientation, and decouple it completely from propellant.
How is that even possible? It sounds like pure science fiction. Controlling a heavy satellite's orientation without any chemical fuel.
It's applied physics.
Yeah.
Specifically, it's leveraging superconductivity. So conventional satellites use these simple copper wire coils called magnetorquers.
Right.
And they interact with Earth's magnetic field to apply a little bit of torque and manage orientation. Xeno supertorquer uses high-temperature superconducting, or HTS, coils. HTS coils have zero electrical resistance when they're cooled.
Okay, what's the tangible industrial benefit of that zero resistance?
Massive power generation efficiency. They can generate a magnetic field up to 3,000 ampere meters squared. That's orders of magnitude stronger than conventional systems.
And that immense magnetic authority.
It allows satellites to maneuver and manage their orientation quickly and precisely without relying on traditional chemical thrusters or delicate mechanical reaction wheels. This fundamentally decouples a satellite's mission life from its fuel tank. And the fuel tank is what currently dictates the lifespan of most small satellites.
So the economic implication is that a satellite's life is now constrained only by the longevity of its sensitive electronics, not by a finite tank of hydrazine.
Pretty much.
But what's the trade-off? You mentioned high-temperature superconducting. How high is that temperature relative to space, and what are the cooling requirements?
That's the engineering challenge. High temperature is relative to liquid helium, which was the original cooling agent for superconductivity. These HTS materials can operate at temperatures that are achievable through passive cooling systems in the cold vacuum of space, or with lightweight, active cryocoolers.
And the power draw for those.
The trade-off is the power draw needed to operate those coolers, but that power draw is still negligible compared to the cost and weight of constantly hauling chemical propellant into orbit. The long-term efficiency gain for a 10 or 15-year mission is immense.
This transition from legacy chemical rockets to nuclear, from big satellites to these razor-thin superconducting disks, it really shows how the foundational science itself is clearing the path for that industrial tempo we started with.
The two are moving in lockstep.
Okay, moving from how we power and design spacecraft to how we operate them. The sources show a universal trend. The space industry is actively handing the controls over to autonomous systems. We are shifting from these highly centralized, ground-controlled operations to a truly self-driving cosmos.
And this validation of operational autonomy, it's non-negotiable for two reasons. First, for deep space exploration, where your communication latency is measured in minutes or hours, which makes real-time human control impossible.
Can't joystick a Mars rover in real time.
Can't be done. And second, for crowded LEO, where automated systems have to react faster than any human operator could ever communicate a command.
And we saw concrete evidence of this autonomy being validated on the International Space Station with the Astronomy free-flying robot.
Yeah, Stanford researchers successfully use machine learning to autonomously pilot NASA's Astronomy. This is not just remote control. This is genuine onboard intelligence. And the key metric here is efficiency, which leads to capability. The machine learning system achieved a stunning 50 to 60% reduction in computation time for complex, maneuvering decisions. And it did that by leveraging prior knowledge.
So the robot is actually learning from experience. It's optimizing its own pathfinding and resource use without being explicitly reprogrammed for every single scenario.
It's orbital muscle memory.
Orbital muscle memory like that.
And this learning is the foundation for future orbital housekeepers, for quality inspectors, for maintenance bots that will operate autonomously on commercial space stations and deep space habitats.
It means they can react to unplanned events.
In milliseconds. A sensor failure, a micrometeoroid strike. They can react in milliseconds instead of waiting for a human intervention cycle that might take hours.
We also saw the Air Force testing systems here on Earth that are directly applicable to orbital autonomy through the X-62 Vista test aircraft.
That's the upgrade to the X-62 Vista with the Enterprise Mission Computer version 2, or EMC2. They're dubbing it the Einstein box.
The Einstein box.
Yeah. And while Vista is an atmospheric fighter jet, the software architecture it runs is critical. It's testing advanced AI agents for multi-agent coordination.
So it's not just about piloting the plane itself, it's also commanding other assets at the same time, like a little fleet of drones.
Precisely. It's demonstrating the ability to pilot while simultaneously commanding a small tactical fleet. And this capability is directly transferable to future orbital logistics.
How so?
Well, imagine a commercial servicing satellite that can fly alongside a damaged asset, diagnose the problem using its onboard AI, and then command a fleet of small robotic repair drones to fix the issue, all autonomously, without any human instruction.
The Einstein box is the software backbone for that.
It's validating the software backbone required for that kind of multitasking and fleet management in orbit.
And we're seeing that coordination capability move from atmospheric testing right into orbit with the reality of in-orbit logistics. This week confirmed the commercial readiness of autonomous rendezvous and proximity operations, or RPO.
This was a pivotal moment for the commercial servicing market. Starfish Space and Impulse Space successfully demonstrated the first fully autonomous RPO mission. They brought 2 small satellites within a tight window of 12,250 meters.
Okay, 1,250 meters, that's about the length of 12 football fields in space. What allowed them to achieve that level of precision and proximity completely autonomously?
The success relied entirely on an onboard camera and guidance system. It was using machine vision and complex algorithms. There was no human in the loop, no relying on high-latency ground commands. This validates Starfish's navigation suite as commercially viable.
And RPO is the building block for everything else.
It is the foundational building block for everything that comes next. Inspection, debris removal, active component replacement, and crucially, refueling.
This validated RPO capability must dramatically affect the market for life extension services. I mean, what does a 12,250-meter autonomous approach capability really mean for the industry? For something like, say, insurance rates?
It dramatically lowers the risk profile. For years, performing RPO was considered the highest risk maneuver in spaceflight. It often required specialized, manually intensive training and procedures, which translated to sky-high insurance costs.
So by validating an autonomous system,
you standardize the procedure, you reduce human error, you prove reliability, and the stability and repeatability will invariably lead to lower insurance premiums for satellite operators who are seeking life extension or repair. It just speeds up market adoption.
And that, of course, fuels the massive growth in the in-orbit refueling market.
Exponentially. The market for in-orbit refueling is projected to grow to over $1 billion by 2033, and commercial services are already targeting the highly lucrative geostationary orbit very soon.
This moves satellite life extension from concept to reality.
From a speculative concept to an operational revenue-generating service. It fundamentally changes the business model. Instead of retiring a $500 million communications satellite because its fuel runs out, you give it a $1 billion life extension through refueling. You turn a depreciating asset into a long-term profit center.
And that economic shift is entirely enabled by those autonomous RPO systems we were just talking about.
That's the key.
It's clear the money is flowing to autonomy because autonomy is generating this massive long-term value in LEO and GEO. Actually, before we discuss how that infrastructure is actually being built for a permanent presence, this is probably a good moment for a quick word for our listeners on Tomorrow Unveiled. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. The sheer scope of these automated systems is astounding, and it connects directly to how humanity plans to operate permanent infrastructure that extends far beyond LEO, which brings us to.
Right. The policy and infrastructure developments this week show that the vision for Beyond Earth is no longer just exploratory. It's about establishing permanent, self-sustaining human and commercial presence, and with a heavy emphasis on industrial utility.
Let's start with the commercialization of low Earth orbit, which is essentially the replacement plan for the International Space Station.
Yeah.
We saw major progress from the private actors planning their own stations. This will be the primary real estate of this new economy.
Right. Axiom Space completed the critical design review for its first habitable module, AX-H1. Manufacturing is now advancing toward final assembly, with plans to dock this module with the ISS in late 2026.
So this is the first concrete step in that planned transition to a free-flying commercial station after the ISS retires.
The hardware is literally being welded together as we speak. That signals a really high confidence in its operational timeline.
And their primary competitor, Starlab, is also gaining significant momentum, but with a fundamentally different approach. What's the core difference in their competitive strategies?
Well, Axiom's strategy is all about modular growth. You add sections gradually, you leverage the ISS's support structure before you break away. Starlab, which is developed by Voyager Space and Airbus, they secured major development milestones this week and are pushing forward with a single module design.
One big piece.
One big piece. Targeting a launch window around 2028-2029. Starlab's goal is to launch a single, full-capacity module in one heavy lift flight. This presents a different risk-reward calculation, right?
A much bigger bet up front.
Potentially higher upfront launch cost, yeah, but less complexity for assembly in orbit. It offers a faster path to full commercial operation. And these two competing designs, they represent the foundational commercial real estate for the entire LEO economy.
But perhaps the most telling strategic decision of the week, the one that signals a massive pivot in government priorities, that came from NASA. And it involved the crucial Viper lunar rover mission.
This was a stunning pivot. It tells us exactly where NASA's head is at strategically. The agency had previously canceled the Viper mission,
Which is the one for mapping water ice at the lunar South Pole, a vital resource.
absolutely vital for sustained presence. But they revived the project by awarding the launch and delivery contract to Blue Origin.
And the change in vehicle is the key signifier of this strategic pivot, right? It's not just that they revived it, but how they chose to do it.
Absolutely. The contract, it's valued at up to $190 million, and it uses the much larger Blue Moon Mark I heavy cargo lander. The significance is profound.
What's the message there?
NASA is signaling that it is moving away from supporting smaller, riskier commercial entities that may or may not succeed. Instead, it's prioritizing the guaranteed delivery of heavy industrial-grade infrastructure. They're choosing certainty and capacity over competitive risk-taking.
So it's moving away from small steps and toward building heavy infrastructure necessary for utilization.
The goal now is industrial presence and resource utilization. You use a heavy lander because you are delivering rugged equipment needed for high-volume tasks.
Like what?
Mining lunar ice, establishing permanent power generations, supporting sustained habitation. It's a complete shift in institutional mindset, moving from flags and footprints back to industrial foundations and resource security.
And policy is actively reinforcing this industrial, utility-focused shift. The political landscape was heavily influenced this week by personnel changes and new executive direction that links the civil space program directly to national security.
Right. The Senate confirmation of Jared Isaacman, who is a prominent commercial astronaut and entrepreneur, as the 15th NASA administrator, that signals a commercial-first approach at the agency's highest level.
So he inherits an agency that's poised to.
To cut bureaucracy and rapidly accelerate public-private partnerships. to directly apply the industrial tempo of the private sector to government goals.
Which aligns perfectly with the new executive order ensuring American space superiority.
That order has two major immediate implications. First, it streamlines authority, consolidating space decision-making to facilitate speed and decisive action to match the cadence of this industrial era.
And the second implication.
Second, and more critically for global stability, it explicitly links civil exploration goals to missile defense. It calls for the development of an Iron Dome for America using space-based assets.
And that blurring of lines between civilian space at NASA and military space at Space Force. That has to raise some profound questions about future international collaboration. Why would an executive order linking exploration to missile defense cause unease among international partners?
Because for decades, the peaceful use of space has been a cornerstone of international treaties. By integrating civil exploration like building permanent bases or placing power reactors with strategic military objectives, you immediately create a dual-use architecture.
So other countries might see a civilian lunar base as a potential military outpost.
Exactly. Nations that are wary of participating in or contributing to a U.S.-led military-linked space infrastructure, even if the civil side is separate, they'll pull back. It jeopardizes cooperation. This move reinforces the industrial tempo, but it increases geopolitical friction and could lead to competing rather than cooperating international infrastructure efforts.
Okay, so for all the staggering progress we've discussed, the nuclear fuels, the autonomous robots, the record launch cadence, the heavy lunar infrastructure, the sources reveal a major crisis brewing just underneath the surface. The long-term viability of this whole commercial space boom is threatened by the very success of its industrialization.
The most immediate and frightening risk is the lack of mandatory shared space traffic management, or STM. The industrial pace has simply outrun the regulatory structure. And this was brutally illustrated by a near-catastrophic incident this week that should be a chilling warning to every single operator.
Detail that incident for us, because at orbital speeds, the term near miss takes on a terrifying new definition.
It does. A Chinese satellite passed within a mere 200 meters of an operational SpaceX Starlink satellite.
200 meters.
Now, to give you context, at orbital velocities, the relative crossing speed between two satellites can be over 14 kilometers per second. That's over 31,000 miles per hour.
At that speed, 200 meters is nothing. It's a blink.
It's negligible. If a collision had occurred, the resulting debris cloud would have generated thousands of pieces of space shrapnel, immediately threatening the entire LEO environment.
That is a recipe for a localized Kessler syndrome event. So what was the root cause? Was it a technical malfunction?
No, it was a failure of diplomacy and data sharing. According to the cross-corroborated reports, the Chinese operator did not share precise trajectory data or ephemeris prior to their deployment maneuver.
An ephemeris is essentially the mandatory shared flight plan for satellites.
It's the address book, the flight plan, exactly. Without that precise, up-to-date flight plan, Starlink's automated collision avoidance system had virtually no lead time to calculate a reliable maneuver. It was flying blind.
So the technology for collision avoidance exists. The autonomous systems can react, but the international will to share the data is voluntary, it's failing, and it's actively creating this dangerous gap.
That's the problem. We are relying on voluntary data sharing to manage what is now an industrial-scale traffic environment. And this highlights the dangerous, growing gap in international STM. Automated machine-to-machine data exchange standards for all operators in LEO are quickly becoming an operational necessity.
And if we can't resolve this issue of terrestrial geopolitics creating orbital friction,
the threat of a cascading collision event where one accident triggers another and another, that remains the single greatest risk to the entire beyond-Earth economy.
And the sheer volume of satellites is also creating this intellectual conflict that pits commercial expansion directly against fundamental scientific research. The conflict with astronomy is reaching a boiling point.
Yeah, new studies quantified the devastating, almost total impact of these mega-constellations on certain scientific disciplines. The data point is shocking, and it is the ultimate realization of the tragedy of the commons.
What did the studies find?
If all the planned constellations are fully deployed, the studies indicated that over 33% of Hubble's images and up to 96% or more of exposures for future wide-field observatories, like the Chinese Zhentian Space Telescope or NASA's SphereX, could be ruined. Ruined by bright satellite trails reflecting sunlight.
That's not just a minor inconvenience. That's functionally destroying years of scientific discovery before the telescopes even get their primary data.
Yeah.
What are the current attempts to mitigate this, and why aren't they enough?
Well, operators have attempted mitigation efforts like applying darker, less reflective coatings to the satellites or angling them during twilight hours, but the volume is just too large.
It doesn't matter if each one is a little dimmer if there are thousands of them.
Exactly. When you have tens of thousands of objects in orbit, even if each one is slightly darker, the collective effect still overwhelms these sensitive scientific instruments that are designed to look at the faintest light sources in the universe.
So the industrial imperative for global broadband is actively working against the scientific imperative for fundamental research.
And there are currently no robust international mechanisms powerful enough to resolve that conflict.
Finally, we need to acknowledge that even at peak industrial cadence, the technical environment is still unforgiving. We saw two major reminders of technical risk this week that underscore the fragility of the entire system.
Yes, reliability remains a constant, brutal challenge. Rocket Lab had to launch abort right at engine ignition because of a sensor anomaly, force an immediate shutdown.
And Blue Origin had a scrub.
Right, Blue Origin had to scrub its NS-37 flight, and that was particularly poignant because it delayed the historic flight of the first wheelchair user to space, Michaela Benthaus.
And it was a technical issue.
A delay caused by a technical issue found during pre-flight checks. It just underscores that even suborbital missions require absolutely flawless execution. We need to remember that these failures, even small ones, contribute to the debris risk. Every anomaly, every piece of hardware that partially breaks up adds to the physical deterioration of the orbital environment.
Which is why the European Space Agency's zero debris approach, targeting 2030, is such a critical international goal.
That target reflects the international urgency to get ahead of the debris curve. They're aiming to mandate systemic changes in satellite design and disposal.
Like what?
Things like guaranteeing satellites are incapable of fragmentation and mandating propulsive deorbit at the end of life to ensure that all new missions contribute zero new debris. The industrial age in space demands industrial-grade environmental accountability, and that regulatory framework is lagging way behind the technical capability.
That seems to be the theme of the week.
It really is.
So, to synthesize the core findings of this incredibly pivotal week, where do we land?
We have definitively crossed critical thresholds.
Yeah.
The 30-flight booster milestone proves reusability is now industrial scale. The autonomous RPO validation proves the technology for in-orbit services actually works. And the GA-EMS nuclear fuel test proves the material science is ready for deep space transit.
So the key insight for stakeholders
Is that infrastructure from nuclear power and refueling systems to commercial space stations is now transitioning rapidly from the construction phase into actual industrial operation. The beyond Earth economy is operational. It's on.
But the shadow hanging over this incredible moment is the lack of governance. It's the failure of international cooperation. We've proven we can industrialize space, we can send rockets up hundreds of times a year, and we can fly them autonomously.
Right.
But the lack of mandatory shared rules for traffic management and debris mitigation, as highlighted by that terrifying 200-meter near miss caused by data failure, it means that the biggest threat to the beyond Earth future isn't technology. It isn't even physics.
It's us.
It's terrestrial geopolitics and regulatory failure.
Which raises a powerful final thought for you to consider as you process all this information. We're building these astonishingly capable self-driving satellites and automated systems. Will the autonomous satellite of tomorrow eventually have to solve the problems that human bureaucracy couldn't? Will they have to develop their own ad hoc automated rules for orbital interaction just to survive?
A fascinating and slightly terrifying thought, that the machines may have to govern the space we inhabit if we fail to do so ourselves. If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
It really does.
And we love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about that aggressive shift toward nuclear power in orbit and the geopolitical friction it creates. It's a fascinating topic for the future of Tomorrow Unveiled.
Thank you for joining us on this deep dive.
We'll see you next time on Tomorrow Unveiled.